Welcome back. The third speaker of this section is Professor Rongjie Lai from Tokyo University. The topic of his talk is learning manifold-structured data using deep network theorem and applications. Let's welcome.
Thanks for coming and thanks so much for the introduction and also invitation from the organizing committee. It's my great pleasure to share some of our recent work about learning manifold structure using deep networks. This is a collaboration with my collaborators and the students. I will mention their name for different topics. I will basically share you, maybe due to time, I'll try to share the first one. If I have time, I will share the second topic. So the first one is the assumption that we assume data is sampled near a lower dimension manifold in a high dimension space. We're trying to understand how the deep network can really learn the manifold structure. So for the second one, our assumption is that actually each data point is a two-dimension manifold, and you have a family of the many two-dimension manifolds. Then how do we design convolutional neural network to conduct a computation on the two-dimension manifold? So let me focus on the first one and see how it goes. So as many of you notice, and recent years, and deep neural network is like extremely popular. I put the three different picture here is like a three milestone. One is the AlphaGo, and then AlphaFold now more recent 2 years, and the ChatGPT. So just make sure we're in the same page. The architecture of the network is actually relatively easy. It's a composition of a bunch of simple functions. So you have a linear functions and the Wi and the Bi, the parameter or the weight of the deep neural network, and theta is some kind of nonlinear activation function. You put them together, then you basically use this as a representation or parameterization of the function you are interested in, and you do the training. So you have some kind of a loss function. So for a simple example, this h you can view as a L2 norm squared. Then you just do the training, and after training is done, you know you got a representation of your function, and you can use this function to do inference. So simply speaking, the deep network is nothing but use a way to parameterize the function you are interested in. So as I said, so essentially all this deep network, to me, is like two essential tasks. One is approximate of the functions. So you have some kind of unknown function defined in some space. So you say, I'm going to use a special function class. And this is not the really new idea, right? Previously, people, when we do the numerical PDE, for example, use a finite element method, or finite difference method, or use a spectral method. People already use different kinds of bases. And here is a sort of nonlinear type of representation. And the other one is if you think about the operator learning. So the object that you would like to approximate is some kind of operator between two, let's say, function class, for example. So if you think about in practice, this space X is usually high dimension. For instance, when you do the image processing, you say ImageNet, the dimension of the axis could be extremely high, it's 1,000 and 1,000,000 dimensions. And if you think about do the operator learning for instance, PDE, and X and Y could be infinite many dimension Hilbert space. So on the other hand, if you think about this very simple statistical arguments, so basically the approximation accuracy is exponentially depends on the dimension of the space. So this is so-called cursor dimensionality. So we'll say the simple example. So if your dimension is 1, you use 100 points, you can achieve such an accuracy. So when the dimension is higher, like 20, you use 100 points, you can only achieve that. If you want to achieve a very high accuracy, you need to sample tons of points, lots of points. So therefore, essentially, according to this arguments, essentially the number of points you need is actually exponentially depend on the dimension of your problem. So, but there's a little bit of conflict if you think about the practice. Deep network actually work reasonably well for the problem. Let's say for image processing, right? The ImageNet. So you have an image, the RGB, you have 3 channels. Let's say, for example, the image resolution is 224. The dimension of the problem, you stretch the image as a vector in a high dimension space. Dimension of the problem is like 224 by 224 by 3. It's extremely high dimension. And if you think about this table and the sampling or the training data you need to approximate the function reasonably well is like extremely, extremely large. But in practice, it's actually different. So you don't need that. Oh, I'm sorry. I used some previous slides. So this should be Purdue. Okay. So in practice, this is not exactly the case. So one sort of idea people do the explanation, roughly speaking, people have such an expectation. Say, hey, maybe there's some kind of lower dimension set up in your real problem. Let's say if you do this the handwritten digit amnest data set. So what you do is each image whose resolution is 28 by 28. So you stretch it, it's like around 728 dimensions vector. So you each image you search a neighborhood, you compute the PCA locally. That will give you the estimation of the local dimension of the tangent space, roughly tell you the dimension of the manifold. So people have several papers say, hey, this guy is actually occupy a very low dimension. It's actually something in a very low dimension manifold. So that's why people say, hey, maybe the reason the deep network work reasonably well is because the problem, although the ambient space is very high, the little m is very high, but the intrinsic dimension, if I call it D, is reasonably small. So therefore, we expect the complexity actually depends on the intrinsic dimension, or exponentially depends on the intrinsic dimension, not the ambient space dimension. That's the expectation. So people say, hey, this might be the reason, and deep network can automatically adapt the manifold structure, and therefore it performs reasonably well. So what we're trying to do is the following. So let's do some theoretical analysis. So let's assume if we really have the data sampled, or have a bunch of points sampled on unknown d-dimension manifold in the m-dimension space, can deep network really learn this reasonably well? So that's the task we're trying to do. Okay, hopefully my message is clear. So there's some rich literature in conventional manifold learning or machine learning techniques, so not deep network-based approach. You may heard many of such names like ISOMAP, LLE, Laplace map, and diffusion map, and all those people have a different estimation dependent dimension of the data manifold, but those are not deep learning-based approach. So on the other hand, more recent years, you may heard this universal approximation theorem and so on and so forth. People do have some approximation analysis about the function defined on the manifold. So what we're trying to do is understand the approximation of the data manifold itself. Not the given the data manifold, you have a function and you understand the approximation function, or understand how the deep network approximate the data manifold itself. Okay, so that's the difference. So let me say a few words about what we're trying to do about the dimension reduction and the deep geometry model. So a very straightforward way to thinking about this dimension reduction is very well-known approach. It's called the principal component analysis. Maybe all of you know this. So what people are doing is that suppose you have endpoints sampled in the m-dimension space. So what you do is you form some kind of a covariant matrix. You compute the SVD factorization of that matrix. You got a D principal component. Then you can do the projection. You have a given x. You compute the inner product of your x with the principal components, and you have the coefficients. Then you have this is the components, this is the coefficient. What you do is you have this called encoding and decoding procedure. Given the data, this is the ambient space. So if your data is actually occupied by some kind of linear structure, subspace structure, what you do is from your D components, you can compute the coefficient, compute inner product to give you the D coefficient. That you can call this D latent variables, and you can have the other kind of procedure. If I give you this D coefficient, you can multiply the components and put them together. You can go back to the ambient space. This is called decoding. So this is a very well-known conventional approach people use for the principal component analysis. And in fact, even in numerical PDE, people use this way. If you fix some kind of dictionary, this UI, for instance, could be finite element basis, or this UI could be spectral, some kind of eigenfunctions of some operators, and you can use this to do a model reduction, which I will mention that in the very end for the nonlinear model reduction. So the way people in a deep learning or deep geometry model is a slightly generalized way in the sense that, so in this way, what I do is I form my data, I form a covariant matrix, I compute this U1 to UD, I fix them, I do encoding and decoding. So there's another way, it's called the auto-encoder, or it's generalization called the variation auto-encoder. They're trying to do the following thing. Say, hey, if I have a point in ambient space, I'm trying to optimize and learn a procedure is from the high dimension to the low dimension, I call it encoding. From the low dimension back to the ambient space, I call it decoding. And my E and D is some kind of deep narrow, as I mentioned before. You parameterize it by your weight, W and B. Then I just say, given the training data, Xi, I want to learn the encoder and decoder. I solve this optimization problem. After optimization is done, I have the DI and EI, and then given new data, I can do the encoding and decoding. So as simple as that. Okay, so the difference between this guy and that guy is this is a linear procedure, right? Because once the UI is given, then all this is a linear procedure, but this one is non-linear procedure. So you can view this as a linear model reduction, but this one is a non-linear model reduction. So this auto-encoder and its generalization called the variation auto-encoder is one way to parameterize the data manifold. So I'm going to, based on this auto-encoder, to do analysis, say how the deep narrow can learn the manifold structure. Okay, hopefully I'm still clear. So before I do that, let me show this very simple yet very illustrative example, which actually motivated our study. So that was a couple of years ago. I asked my students to try the following thing. Okay, suppose I have some data manifold. This is my data manifold, which is sampled on a double torus, whose topology is non-trivial. Actually, Lai mentioned this most small function and can observe. Use a high function, say the most function as well. So the topology of this guy is non-trivial. That's the key. So what my student is doing is the following thing. So this guy is the manifold dimension is actually 2-dimensional. If you think of the parameterization of the manifold, what you need to do is you need to use a 2-dimensional latent space in that variation auto-encoder to use 2-dimensional space to do encoding and decoding learning. So this picture shows you once the training is done, so I can sample new points in the latent space. I ask the decoder to decoding the latent code back to the ambient space. This is a result of the decoding result. So we're using 2-dimensional latent space. So no matter how hard, how much effort you're doing for the learning procedure, as long as your latent space is a Euclidean flat domain. So once the training is done, I sample them. I ask the decoder to go back. So you can see I cannot cover this data manifold. And this one is another example. So instead of using 2-dimensional latent space, I'm going to use 3-dimensional latent space. Once after training is done, I randomly sample point in the latent space, I ask the decoder to go back to the ambient space. Or you can actually, in our experiment, artificially lift this in a very high dimension, although its intrinsic dimension is 2D. So you can see this guy seems like, in terms of coverage of the data manifold, is better because you can roughly see the double torus structure. However, you see some artifacts. Okay, you see some outliers. So think about it if you want to ask the deep narrow to generate a fake new image. So if this is data manifold is a distribution of your image manifold. So in fact, your deep narrow actually generates some image you don't like or not look like not real. So we'll also do extension, try the variation auto-encoder. We try different kinds of architectural variation auto-encoder. So if we choose a 2-dimensional latent space, no matter how hard we're trying, so we cannot cover. So those blue dots, they are training data. And red dots is after training is done, we sample points in latent space, ask the decoder go back to the ambient space. You see, it's extremely hard to cover the data manifold. So this motivates us to think about, as I mentioned before, so how neural network can really learn manifold structure. At least according to this example, it cannot. Okay, so we want to say, hey, maybe theoretically, can we say something, and numerically, can we propose something different to such that this data manifold can be learned? Because in practice, the data manifold here usually has a non-trivial topology. So that's what you need in practice. So, and let me even show you another simple, even simple example, and still have some issue. So this simple example, the data manifold is actually a circle, not even double torus. But the key is also whose topology is non-trivial. So if your data manifold has a circle, I have 2 points, okay, P and Q. So the way, for instance, the way you do the latent space, how do you do? So because your latent space you're choosing is a flat domain, 1D, this is a one-dimensional manifold, you choose a 1D. So what you do is, for instance, you can use cosine and sine. So what you have to do, you have to artificially cut down at some points. For instance, this P and Q, they're very close on the original data manifold. You cut it down, so you artificially distort the distance between the P and Q in a latent space. So you introduce a huge distortion of the metric in latent space, such that this guy, most of the points you can parameterize instead of these 2 points. You break the topology. So one way, I mean, this is actually useful. People say, hey, in this kind of time-dependent problem period, you have some periodicity, and you may observe the object you have some kind of loop space structure. So if you do the conventional way of the latent space and the auto-encoder, it actually cannot work. But there's a nice idea is, hey, instead of doing this using the one interval, you can use a 2 interval. You just shift it a little bit, and each interval you cover, you have some overlap, and put them together, and you have this 2 group efforts, and you can make it happen. So in fact, in practice, people do observe. I mean, I put some literature. People do observe, instead of using this flat domain as a latent space, people observe in practice, you may need the spherical-like latent space, for example, or you may want to parameterize the closed path, or even you want to choose some kind of special Lie group as a latent space. But no matter what, all the existing approach, they have some prior knowledge about the information of your latent space. So either is a spherical structure, or loop structure, or the Lie group, some kind of special SO3 Lie group structure. So we're trying to say, hey, if your data manifold has some general structure which we don't know, can we still theoretically say, hey, there exists a network to approximate such a data manifold, and also computationally, can we design something to approximate such a manifold? Then I will show some applications. Okay? So as I said, our objective is, suppose we have endpoints sampled actually nearby, because you may have some noise, nearby a d-dimensional manifold in the m-dimensional space. So we want to ask whether there exists a network. As I show you, if you naively do it, it does not work. Whether there exists a network such that the approximation error is reasonably okay, and also once the training is done, you want to ask for those points not in your training data set, what's the generalization error? So as I said, whether exists such a network can approximate the data manifold. You can call this universal approximation theorem of the manifold, universal manifold approximation theorem. What's the complexity, as I said? So we hope the complexity depends on the intrinsic dimension of the manifold, or exponentially depends on the intrinsic dimension of the manifold, not the ambient space. Not exponentially dependent on ambient space. Otherwise, that cannot explain why this works well. And also, we want to design a computational tractable method. Hopefully, our method also robust to noise. So that's what we're trying to do. So let me see a few words what we can achieve. So first of all, we observe, as I mentioned, if you have a non-trivial topology, actually the conventional approach does not work. So we propose such a very simple concept that we call the fistful representation. So the idea is very simple. Suppose you have an auto-encoder. So if you have such an auto-encoder, if every point on the data manifold after training is done, if every point on the data manifold you can 100% reconstruct, this is called the fistful representation. Of course, this is not achievable, and we call the autoencoder is called the epsilon fistful representation. If after training is done, for all those points outside of the training data, so our infinity norm is less than epsilon, we call the epsilon fistful representation. We can actually theoretically show if M is a d-dimension compact manifold, if you have an auto-encoder, such that this auto-encoder is epsilon faithful representation with this epsilon less than the reach of the manifold. The reach is some kind of condition number of the manifold, which is essentially related to curvature. If for example, if you have a flat space whose reach is infinity, so if you have a hypersphere whose radius is r, whose reach is r, the bigger radius than the bigger reach. If reach is very high means the manifold is very flat. So if the reach is very small means the manifold is very oscillatory, the curvature is very high. Okay, so we show if your data manifold, if you do this kind of, if you ask your reconstruction error is epsilon faithful such that the epsilon is less than the reach, then the latent space and the manifold must be homomorphic. So in other words, if your data manifold has a non-trivial topology, there's no hope you use a conventional method to parameterize your data manifold. So the latent space has to be homomorphic to the data manifold itself. So this theorem tells us, this motivated us a new design of the network structure. Instead of a conventional autoencoder, we need to do something else. Okay, this is a sort of theoretical investigation. The conventional method does not work. Okay, so we want to leverage the idea from differential geometry. They built up such a beautiful theory 100 years ago, and we just borrowed the idea, and it actually works. So in a differential geometry, people say, hey, this is called a manifold. Manifold is actually a connection of the charts. So you have a different charts, and you have the chart parameterization, and you have a translation function between charts. So we can do the translation between the language in differential geometry and the language in machine learning. So this is the data manifold, and this chart, when you parameterize, this is called a latent space, and this parameterization you can call this encoding, and inverse is called decoding. So what we're trying to do is we'll leverage such an idea, but we need to simultaneously learn, instead of a conventional approach, only have one chart, single chart. As I show you, if you use single chart, if your data manifold has a non-trivial topology, single chart does not work. So we want to leverage this multi-chart structure, and we want to simultaneously learn the chart structure and also each chart autoencoder. Hopefully this can help us to overcome such a topological obstruction. So that's the idea. Okay, we can actually theoretically show such a universal manifold approximation theorem. So instead of using the single chart, if the idea is you want to use multiple chart, then it works. So we can show that if you want to achieve epsilon accuracy means after training is done, this is your empirical loss. Okay, you have n points. After training is done, you check all other points not in your training data set. This is generalization error, infinite norm. So if you want to achieve the accuracy of epsilon, you better choose the number of training data is exponentially depends on the intrinsic dimension. So not the ambient space, not the ambient space dimension. That's why we're happy. And also the network structure, the encoder and decoder has this multi-chart structure, and whose number of parameters also intrinsically depends, exponentially depends on the intrinsic dimension. Okay, there is some dependence of the ambient space, but not exponentially. So it's linear. So it doesn't matter. Linearly, we're happy. So the exponential part has to be only depends on the intrinsic dimension, and the number of layer also depends on the intrinsic dimension. Okay. So due to time, I will not talk about the proof. So nevertheless, we show theoretically, if you use this multi-chart structure, then you can actually achieve such approximation. And previously, according to the experiments I show you, it doesn't work. Okay. Now, let me extend to the generalization error. So the previous result is approximation. So nothing to do with training. I just say the capacitive neural network can achieve such a thing. Now I want to say if I have a training set xi, and xi is a noisy data, and vi is on the data manifold. So I do such a training. So I search an encoder and decoder. So this is my empirical loss. So if after optimization, I can have this global optimizer. I want to ask, for this global optimizer, if I check all other points which I don't see in my training procedure, what is the numerical? What is the error? What is the reconstruction error? So This is what we can achieve. So as I said, so once we have the global optimizer of the empirical loss, we can estimate, this is the global optimizer of the empirical risk, we can estimate for all the x, not necessary in the training data set, right? Is anything outside the training data set. So you will see this arrow is actually exponentially depends on the intrinsic dimension again. We're happy. Of course, you have some factor about the ambient space dimension, but it's polynomial. It's quadratic. It's okay. And also number of layers and number of parameters, and all they are intrinsically depends on the exponential part is just the intrinsic dimension. So and also one thing I wanna comment is that so this one, our assumption for this one, we assume the noise is actually along the normal direction. So you will see this auto-encoder is actually when the sample n goes to infinity, so this arrow is gonna go to 0. So in other words, this auto-encoder has some automatic denoising effect. The denoising effect is about the normal direction noise. So we do have some theory about the tangential noise. So we observe the tangential component noise. Tangential component basically stay on the data manifold. The tangential component noise cannot be denoised. So this one, the tangential component noise is always there. No matter how hard you are trying and how many training data you put, at least this architecture or this way, this assumption, we cannot handle the tangential noise, but we can handle the normal noise. Okay? So I won't talk about essentially the idea is to leverage our previous approximation error. So we do approximation error, and also we do the statistics. And this guy, you will see the covering number of the neural network. And this sort of relatively standard analysis, we can achieve such a result. Okay? So now, let me show you, as I said, we first have some theoretical sort of guarantee, and if we use a multi-chart structure, we can achieve such universal manifold approximation theorem, and also use generalization error guarantee. So we want to design some computation approach to solve it. So our computation idea is sort of leverage the idea from differential geometry again. As I said, in the differential geometry, they say approximate the manifold use multi-chart. So one component use multi-chart is called the partition unity. So what we do is we design a neural network to essentially approximate the partition unity, which can tell us data on the manifold belongs to which chart. And also, once you know each chart, you do the auto-encoder for that chart. But the challenge is we need to do this simultaneously. So if you know the chart structure, that everything is just the decoupling of the chart structure as the conventional approach. But the challenge is they're coupled together. So we design an approach to simultaneously learn the partition unity, the chart predictor, P, and also the auto-encoder for each chart. Okay, so I'm gonna skip some technical details. Let me show you the results. Okay, so the first result is pretty simple. It's actually a circle. Topologically, it's a circle. It's a cat. Is the outside of the cat. Okay, so we use a full chart to learn the cat manifold. Okay, so after training is done, you will see this actually is a chart predictor function. The chart predictor function is very similar to the so-called partition unity because they localized on each chart and their summation is equal to 1. This is exactly partition unity because we use a softmax function over there. And you will see each chart nicely decomposes cat to be 4 chart, and each chart you can use this auto-encoder to parameterize them. Okay, so now during the procedure we have some kind of mechanism we call the automatic chart remover mechanism. So because of the architectural network, we need to tell the network how many charts do we need. Okay, so what we do is we always overestimate the number of charts. For instance, theoretically, we know to approximate the unit sphere, you only need 2 charts. So we give the network 4 charts, and during the training, we monitor the value of the partition unity. So if the value of partition unity at some stage is constantly 0, then we shut down that chart. So you will say initially we have a 4 chart. After training is done, we nicely got a 2 chart. So which is compatible with the theoretical prediction, but a sphere will only need 2 chart. Okay, so we can do some slightly more complicated topological structures. Let's say this is my motivation examples. You have a double torus. Okay, previous effort does not work, but if you use multi-chart, actually works. This is after training is done, we sample points in latent space and ask the decoder to go back to the ambient space. You will see it covers the data manifold very nicely and does not produce outliers either. Okay, and this is even more complicated topological structure. Okay, and this picture shows you this approach is actually robust to the normal noise. So this curve shows you, so because we have that convergence rate in terms of normal noise, and it shows you it's actually sort of compatible with our theoretical prediction. So this example is actually very interesting. So we try some real data. So it's called the human motion. It's called gait data. So this gait, I'm not sure if you can see this very clearly. The gait data is the input is like we have the coordinates of the joints. You will see this blue dots. I'm not sure if you can see this very clearly. Blue dots. So each human body shape, they have a different kind of point on the joint, which is green dots. Green dots. That's our coordinates. So the human body shape move in the space. This green dots sort of move periodically in the space. So you can imagine the topological structure of this data set is a product of a bunch of S1 in the space, whose topology, of course, is non-trivial. So as I said, if you use a single chart, you think about my example about circle. If you use a single chart, you have to artificially break down the topology. The 2 points nearby in the data space, you will distort the metric in the latent space such that whose distance will be enlarged or distorted a lot. So we actually do observe such a thing. So this blue one is the conventional approach. You will see we have a 2 consecutive frame. We compute the distance in the latent space, distance of latent code in the latent space. You will see those distance occasionally will jump up, which means think about my circle example. I have P and Q very nearby in the data space, but then because you break topology in the latent space, the distance is gonna be enlarged a lot. So that's actually we do observe in practice. And as a consequence, if you do this reconstruction and you do sampling of the motions, it actually does not work so well. And this curve, the yellow ones are Chart Auto-Encoder structure. So if we monitor the distance, it actually does not have this artificial bump of the distance. So as a consequence, you will see the Chart Auto-Encoder actually produce much nicer periodical motion result than the conventional approach. So this practical experiment show our idea actually works pretty well for this data manifold with non-trivial topological structures. And the next slides I show, we try this for the different kind of image database. This is the MNIST, the fashion MNIST, and many others. So we compare this with the different architecture of the variational auto-encoder. We have 3 different numerical arrows: the reconstruction and unfaithfulness and the coverage. And from the you will see from the similar parameters, number of parameters, and our Chart Auto-Encoder always produce the best one. So which means, so once the data manifold structure has some non-trivial topological information, and you better use some way to twist the design of the neural network, for instance, our Chart Auto-Encoder structure, such that this can improve the approximation of the data manifold. Therefore, they can improve the downstream task. Okay. So am I clear? So now, if you don't have question, I'm gonna mention an extension of such an idea to analyze the nonlinear model reduction in operator learning. So as I said, in operator learning, basically, so for instance, if you think about it, you solve the parameterize the family of the PDEs. So you want to use a deep network to do the to learn a solution operator of this parameterized family. So basically what you need to do is to learn a Lipschitz operator between two Hilbert space. Okay, so this will be a solution operator of some kind of PDE, for instance, Poisson equation, for instance, KdV equation, for instance, transport equation. So what we're trying to do is we want to set up a theoretical analysis, say whether deep network can work or work in what sense, such operator learning technique can have some kind of theoretical guarantee. Okay. So our assumption is the following: suppose you have a Lipschitz operator between two Hilbert space, and this Vi is, you can view each Vi as for instance the solution of some kind of PDEs, and Ui could be the input of a PDE. For instance, you do a transport equation. I will show you an example later. For instance, Ui could be initial value of your transport equation, and Vi could be the terminal value of your transport equation. So this network give you from the input, give you output. Okay. So you wanna ask if you have some noise perturbation of the input, and also because this guy is in the Hilbert space, you have some numerical PDE discretization of your differential operators. This is your Sx and Sy is your discretization operators. So you want to say if this guy, your training data is sitting in some kind of lower dimension manifold in this Hilbert space, as I said, the error and effort you need to make is actually exponentially depends on the intrinsic dimension of your data. So the practical assumption is your data is actually sampling in some lower dimension space in this infinite many dimension Hilbert space. So think about this model reduction approach. You use let's say you choose use a spectral approach. You choose the eigenvector of some kind of operator. You use like hundreds of eigenvectors, and you hope your system is actually, you project to that linear space as a reasonable assumption. It has a reasonable accuracy. So this is basically sort of the assumption here. So you have some kind of nonlinear lower dimension manifold assumption in this Hilbert space. So our idea is we want to propose sort of two-stage approach. The stage one is we have this so-called nonlinear model reduction stage. So you have once you have the data set, so you discretize them. So you have a D1 capital D1 dimension space, and use some autoencoder to learn the intrinsic data manifold structure of your data set. Okay. Now once the autoencoder can be learned, then you learn the operator, you learn the solution operator in latent space. So we want to ask, if you put those two stages together, what kind of theoretical guarantee you can have? Okay. So some kind of assumption. So we assume your discretization operator is actually nice enough. Well, this is actually a very mild assumption. The discretization error is actually bounded below and above by some constant of your true error of your function. And also, we assume your data has some kind of lower dimension manifold structure. So the data M is actually a D-dimension manifold in the Hilbert space, can be parameterized by the auto-encoder. So with this assumption, we can actually theoretically show two things, as I show you. One is the universal approximation theory. We can show with for any choice of the epsilon 1 and epsilon 2, your network parameter only depends on, exponentially depends on the intrinsic dimension of your data manifold. Then you can achieve such approximation error. Okay, and also the learning operator can be also learned for any given epsilon 3. Your learning operator can be also learned with those parameters, and the key, as I said, the key is those parameters only depend on the intrinsic dimension of your data manifold. That's the key. So the data, although your data manifold could be sitting in the infinite many dimension space, but as long as its intrinsic dimension is little d, and this is the sort of the effort we need to have. So this is to show you the capacity of the network. The second one shows you the generalization. So the idea is, as I said, once the training is done, you want to check, you're plugging your neural network due to prediction for those data you don't see. Okay, and this generalization error also tells us this generalization error also only depends on the intrinsic dimension of your data manifold. Now, all this actually, this is first such a theory to show if you use this kind of architecture, we have reasonable theoretical guarantee can achieve for the generalization can achieve such an error. Okay, so let me quickly show you some simple numerical results. So I show you different types of equations. The first equation is about the transport equation. Very simple transport equation. So our input is the initial value of this transport. Basically, have a gx. You after time t, you just transport the initial to some point, some solution. So we want to learn from input to the output. So our input is actually we sample the input function. This is actually the way we sample the input. I have two heads, and we randomly choose the alpha and a. Randomly choose a and h. Okay. So this picture show you our stage one, the auto-encoder, the neural manifold structure stage. So you will see we can nicely learn this data manifold, and this color coding show you the a parameter and the h parameter, and also this show you the comparison between our method and also the conventional model reduction, linear model reduction approach using PCA based approach, and is actually the nonlinear model reduction based approach using deep network actually can produce a better, much smaller error. And similarly, we can try the Burger's equation with some viscosity. The viscosity parameter is 10 to the power minus 3. And also, this picture also show you if you use we can learn the lower dimension manifold reasonably well. And this is the lower dimension manifold structure. And this is the color coding about the parameter. And also we compare this with the conventional linear model reduction approach. And this is our auto-encoder based approach. You will see auto-encoder based approach whose error is actually much smaller. Especially this guy, we purposely designed the data manifold as actually two-dimensional manifold. But if you use a PCA, the linear model reduction based approach, the PCA you need many eigenmodes. So if you just say the two dimension here, so the error of the PCA actually is very bad. But our method still produce a reasonable numerical error. We try the KDV equation as well, and also many other equations, but I don't really show here. The similar phenomena you can observe, and the idea is again, if you only use the linear model reduction based approach, you may need to use many eigenmodes. But the nonlinear model reduction actually give you a reasonable approximation error, even because the data manifold is a two-dimensional data manifold, but it's not a linear. It's two-dimensional nonlinear structure. You cannot hope to use a two-dimensional linear structure to approximate. Therefore, you may need to use many eigenmodes if you use PCA. And this table actually show you the comparison if you use different kinds of dimensional latent space. You compare with the AE net and PCA net and also deep O net. So you can observe whether you use a PCA net or deep O net. If the dimension of the latent space is not big enough, the error is actually not very nice, especially the deep O net. So if your dimension is not that big and the error is actually really bad, right? This error is 96%, but ours is like 1%. Okay, but as long as the latent space dimension is increasing, so you will see the deep O net, the numerical error actually improved. But of course, the higher latent space dimension you are using, the much more computation cost you need to provide. Okay. So I have a couple minutes. Let me share you a story too about the sort of now the story is each data structure is actually a manifold. So previously each data structure is just a vector. You have a collection of such a data structure. You form a high dimension manifold. We want to understand how the deep network approximates such a manifold structure. And this one is motivated by computer graphics, computer vision problem. especially the 3D processing. I have a collaborator in our university. He has the expertise to basically scan 3D structure in the space. So we want to process the 3D structure. So you have a different kind of 3D structure you need to do. For instance, this MRI imaging like human brain. So you have you scan the MRI image, you form a basically two-dimensional remaining manifold in a three-dimensional space. You want to process them like different kind of human structure. And also, for instance, here people talk about autonomous vehicle. So when you drive a vehicle on the street, you online to sort of scan the 3D point cloud. You want to process the 3D point cloud. You want to do the comparison. You want to do the recognition, and so on and so forth. So we want to design a machine learning approach to handle such a 3D structure, or it's actually two-dimensional manifold in a three-dimensional space. Okay. So to handle this kind of spatial structure, one very powerful approach is so-called convolutional neural network. It's very well known, and if you want to handle image, right? So you do the convolution network to do the image processing. And the nice thing of the image is actually the two-dimension R2 is spatial invariant. So therefore, you can write down such a convolutional operator, and you can do the convolutional neural network to design a neural network structure. So unfortunately, and this kx minus y can only be defined on the spatial invariant structures. So in our two-dimensional manifold in 3D space, there is no x minus y structure. For instance, think about sphere. So if there's no ambient space, you cannot talk about 2-point do the subtraction on the sphere. It will not really stay on the sphere at all. So there's no x minus y structure in the curved manifold structure. So people design different kind of approach. One of the very popular approaches is called a spectral-based approach. Basically, you solve a Laplace-Beltrami eigenfunction on the manifold, and you process the eigenvalue of the Laplace-Beltrami eigenvectors. You do the filter on eigenvectors, and there's some good and bad for those spectral-based approach. Basically, I described here is not actually transformable, and also is not deformable. So we want to design some kind of a spatial way of do the convolution on the manifold such that we can process this one to mimic the convolutional operator in the Euclidean space. So that's the idea of this kind of research. So let me quickly say how do we do that. Due to time, maybe I will just tell you the idea and I'll jump to some results for fun. Okay. So the idea to redesign a convolutional operator from the Euclidean space to the manifold is actually rethinking the convolutional procedure. So if you think about the Euclidean space, you have two functions. The convolutional operation is you have a kernel function. You do such integration in the Euclidean space. Okay, if you think about what is the x minus y. So basically, x minus y is doing the following thing. So x minus y is you need to figure out the vector field in the space. So sitting from this compact domain, you want to shift this to this new domain. So the shift in the Euclidean space, you use x minus y. But this shift is nothing but x minus y is some kind of vector field. You take a derivative, the derivative is a constant, it's 0. So therefore, you see the subtraction. Okay, so that's basically the way to rethinking. So we want to, based on this rethinking, to design a new way of doing the convolutional operator on the manifold. Therefore, we can design different kind of a convolutional neural network on the manifold to do manifold processing. That's the basic idea. So once again, the idea is use rethinking x minus y as x minus y is a vector field. So this guy is basically you transport the vector field from here. I have every point here. You transport this vector field from this domain to this domain, and you take it. The minus is just take a derivative is equal to constant. So in the differential geometry, there's exactly the same idea as I explained. You can do the transport in the following way. So basically, you can say I have a vector field. I can transport the vector field on the manifold such that the derivative is equal to constant. So this is called a covariant derivative. So basically, what you need to do is you need to design some way to compute this covariant derivative. Then you can, for each vector field, you can do the parallel transport on the manifold, and then therefore you can sort of shift your convolutional kernel from one point to every other point. So I won't tell you the technical detail. Basically, what we do is we solve some iconic equation on the manifold and use that to have a geodesic vector field and use the geodesic vector field to propagate the information on the manifold. Nevertheless, this is the picture we can obtain. So you have some curved manifold in the space. So starting from, I intentionally put this anisotropic convolutional kernel on the manifold. And you can do the translation of the kernel on the manifold, not rely on ambient space. You can do the dilation, you can do the rotation, you can mix them together. So now the remaining task you need to do is just design some architecture to learn such a kernel, as the way people do in the Euclidean space to learn the convolutional kernels. You can do multiple kernels, you can design convolutional neural networks. So let me show you the different kinds of applications. The first application is do the manifold registration. So you do recognition, right? You have a group of two-dimensional manifold in a three-dimensional space. So you want to extract some invariant features, such that using this invariant feature, you can do the recognition. So how do you do how do you extract the invariant features? One conventional way is I used to do this is called the spectral geometry. You solve the Laplace spectrometry eigenfunctions for each of them, then you compare use the spectral geometry, you compare the eigenfunctions. Now, if you have the way to design a convolutional neural network, what you do is instead of using the fixed differential operator, I'm gonna use the data-driven way to learn the convolutional kernel, then to learn the feature function. So you design a neural network architecture. So based on our parallel transport convolutional kernel, and this is actually the result learned by the neural network. So you will see it actually cross different manifold. So this different manifold has two distinct distinction. One is that they have a different pose. Different pose means they have a different normal direction. They have different extrinsic informations. Okay, so remember when you input this to the computer, what you input is this XYZ coordinates. So even the same human body shape, you have a different pose. Computer will see they are different. But the challenge is you need to extract the invariance such that even the same human body shape with different pose, you want to see they are the same. Second is some of the human body shape they are thinner, some of them they are wider. So it means they have a different metric. They have a different metric, which means they have different intrinsic information and different extrinsic information. You want to learn them to extract the invariant features. So this is actually the invariant feature learned by our parallel transport convolutional kernel. So once you have these invariant features, you can compare them in the feature space. And you do, for instance, you can do the optimal transport in the feature space. So this curve tells you can build up the mapping. You can, based on the feature space, do the registration. And this geodesic arrow, the higher of the curve means the more accurate you have. So you will see this is actually our approach. This is some other approach. Okay. So you can do some other tasks. For instance, you can do the deformation of the manifold in the space. So what you do is, so remember, according to our elementary differential geometry, if you want to reconstruct a manifold, a two-dimensional manifold in the space, you need two ingredients. One is the Gauss curvature. The other one is the normal direction. So it's actually guided by the so-called Gauss-Codazzi equation. So, but this equation is actually highly nonlinear. It's not easy to solve. So now we want to say, hey, if we can use this parallel transport convolutional neural network to sort of deform the manifold in the space. So here's the one. So you have the source manifold, you have a target manifold. The challenge is that the source and target, they have a different pose. Means they have a different second fundamental form, and they have a different metric. Because one is thinner, the other one is wider. So they have a different first fundamental form. I don't have the correspondence. So I want to say, can I do, basically I use some kind of auto-encoder structure, and then once I learn the latent space structure, I can draw a line in the latent space and I ask a decoder decoding, and this is actually decoding results. You will see this guy is morphing gradually from this one, change the pose, and change the metric. All this video you see is actually produced by deep network. The input is just these two guys. You see, instead of you doing this in the ambient space, will produce lots of artifacts, and this guy nicely preserve the shape of the geometry and give you a very nice natural looking. Another one. Animals, the same. So you have a source, you have a target, and you can mimic. Well, we don't really include in the dynamic yet, but we can do we are working on learning the dynamic as well. But nevertheless, this picture shows you can deform the one manifold to the other manifold based on the geometrical way of the design of deep network. Okay, one more extension is we can do the point cloud processing. So we actually extend this parallel transport on the point cloud using this level set based approach. It's called narrowband. Once we have that, then we can do different kinds of things. We can do the classification and the segmentation. This paper is a couple of years ago. At that time, we're not for the classification. The overall accuracy were the best, but the mean per class accuracy were also reasonably good. For the ShapeNet part, I think we're not the best, but we're the second best. Okay, this is the classification and the segmentation. We can also try for this sort of robust test for the real data. So we can segment this real 3D data. So we are, for the overall accuracy, we're doing reasonably good. Actually, we're the best using the compare all the geometric way of the convolution. And for the mean class accuracy, we're not the best, but we are the second best. Okay, so my time is out. Let me wrap up. So to summarize, basically I tell you sort of two stories based on the geometric inspired designing of the deep network. First, we propose a multi-chart latent space to understand why the deep network why and how the deep network can approximate non-trivial topological data set. And we extend to the model reduction to study the operator learning in the PDE setup. We also propose a spatial way of the defined convolution on the manifold using parallel transport. And I show you different kinds of application about the shape processing, like about shape matching, geometric disentanglement, point cloud classification, segmentation, and so on. And here are all reference. Thanks so much for your attention.
Okay, thanks, Professor Lai, for the wonderful talk. Any question, please?
Thank you. A very nice talk. And I want to know, for training your series neural networks, what kind of method you are using?
Which one?
There are some of them.
Oh,
right?
I mean,
encoder, decoder.
Oh, that one we just use Adam. Very naive approach. We don't really try any fancy stuff.
Okay.
Just use the
use
existing.
It's a fashion.
Yeah, actually the key is not the training method, but some kind of regularization we impose. I actually ignore such a detail. So we need some kind of regularization to guide the Lipschitz constant of the mapping. Otherwise, you will see lots of huge distortion when you learn the manifold structure.
Okay, but you know, some research told that Adam have some problem in generalization. So have you suffered?
For this one, we don't really observe something really bad. So all this just trained by Adam. I mean, actually all this results are trained by Adam. It produces a reasonable good result, and even in like this practical data.
Okay. Yeah. Okay. Thank you.
Two very quick questions. So the first one is about the first part, when you assume actually the encoder decoder is automatically provided by solving the global optimization problem, right? So, but that's not convex problem. So, so in general, you cannot assume the solution can be found. So, in practice, do you see the possibility of make your result more general under the scenario that the solution of the optimizer is not solved?
Xiaoming asked a very nice question. Actually, I don't know how to do it. You are expert. You should tell me. So because there's a part of basically the proof techniques, technique challenging a proof. When we do the generalization error, when you use some kind of triangle inequality, and if we assume that's a global minimizer, tell some sort of easy way to handle that triangle inequality. But if we if we don't have that, that part cannot go through. But I agree with you. In practice, to me, at least to me, maybe optimization is one of the if not most challenging, at least one of the most challenging problems in the deep learning. People just don't know. I don't know how to do it. Yeah. You got a global minimizer. You have any idea that will be?
I have no idea, but I know this is a common problem actually for many of these workers.
We do have some kind of people use for instance, some kind of Longitudinal dynamics, put some random noise, like a leading type of thing, but it's very slow. We have some recent idea about distort the metric about the netscape of the loss function, but that has some limitation, not general class.
Yeah.
I think that's a huge problem if anyone can solve that.
Yeah. Okay, my second question is about the second part of your talk. When you show us some examples, like the applications for the human, for the movement of the human, right?
Yeah.
So have you considered the application to the hair, similar the hair of a human? I'm working on this problem for industry. Actually, that's a very, very important problem for industry.
No, not yet. Not yet.
Do you think it's possible to?
Oh, it depends on resolution, right? If your resolution, the hair of the resolution is reasonably okay, that's. But so two things. One, the resolution. So you need to. So this one we assume this one either parameterized, either represented by point clouds or triangle mesh.
Yeah.
I don't know, your data set is like your hair is like a point clouds or triangle mesh.
The hair, we have to simulate the hair by elastic rope.
Or it's like a string or something.
String of rope. So the question is actually, first of all, we have to simulate the physics with a lot of variables. Like usually when people has 12,000 strands of hairs in general, and each strand of hair, we need to split it as a 100, 200 variables, rows.
Like a dots.
Yeah, and then we need to simulate a lot of other physics. So it's a problem of million variables, integer variables, by the way. So that's very, very difficult problem. So I'm not sure your methodology can be extended.
I do think this sort of auto-encoder type of thing can reduce number of variables. Yeah. But the second thing we have not really done yet is there's a dynamics. So basically, you need to learn the dynamic in latent space. So this one, we don't really learn the dynamic. We just draw some curve artificially, and you produce. But we do have some idea to try to learn the dynamic in the latent space. Maybe we should discuss.
Okay.
Yeah,
sure.
That's possible.
Yeah.
Thanks.
Hello, Professor. I just got a simple question. I just want to ask, if our dataset contains like 3D figures, will the price we pay for the training process become like very large? Like the time or the storage we should pay on the training process become very large?
Well, so this guy is this 3D is actually two-dimensional manifold in R3. So it's still surface, which the essential degree of freedom is the same as the image. If you can handle image, you should be able to handle this. Even 3D, right, depends on how powerful the GPU you have. Even 3D you can handle it. So I don't think that's an issue. Yeah. And plus if you do this, for instance, this one is a triangle mesh. The number of points of this guy is just 6 to, I think, 7,000 points. Think about the image resolution. If you have 200 by 200, the size is already 40K, right? And this is a reasonable. That's actually another point I did not make is the way you do the spatial of design the convolution, the computation cost the same as when you is the same as you had the two-dimensional image. If you can handle two-dimensional image whose resolution is 200 by 200, you can handle this one. Yeah.
Thanks very much for the talk. I just had a technical question about how you implement the charts learning process. So do you have to train for each chart? Do you have to train a separate network and then select which region?
No. So if you know the chart structure, then you do the auto-encoder. That's easy. The challenge is you don't know. So we actually simultaneously train them.
Yes. So do you need a separate network for each
Oh
chart?
yeah. Well, each chart you have a separate network. Yes. You have a different network. Let's say if you turn chart have turn networks, they have a partition unity as a chart predictor.
Yeah. Okay.
Yes,
Thanks.
they do.
That's how I
They do.
it.
Yeah.
Any more questions? Okay, thanks, Professor Lai again.
Thank you.